Here's the last video. The last video is going to be on related rates of word problems. And when I say the last video, I actually have more videos coming, but this is the last video for me today at this time. Okay, let's go and get going. Water is leaking on the floor, forms a circular pool. The radius of the pool increases at a rate of 4 centimeters per minute. How fast is the area of the pool increasing when the radius is 5 centimeters? What? What the what? What the? What the what? What's going on here, Mr. Lincoln? Good question. You're going to need some tips for this before we actually go on. I would say the first tip, and I don't think these problems are going to get terribly complicated. I'm going to say the first problem is you got to set up a picture for the word problem. Picture for the word problem. Okay, let's do that first. Number 1, tips on how to solve, and write this anywhere you need. Tips on how to solve related rates word problems. Okay, so let's see what we got. Water is leaking on a form that forms a circular pool. Circular, ooh, circular, there's a circle. Okay, we set up the problem. Next. And I was not kidding about that. That's all we could do. Next. Then set up an equation to go with the word problem. This one is easier said than done. Okay, now if it says that water is leaking on the floor, forms a circular pool, the radius of the pool increases at a rate of 4 centimeters per minute. How fast is the area of the pool increasing when the radius is 5 centimeters? Okay, all we know that we have a circle. But what else do we know about a circle? Well, we know circumference, I hope. Circumference is 2 pi r. We also know area. Area is pi r squared. The question is saying how fast is the area of the pool increasing? Well, the area is this formula. So that tells me I'm going to use area equals pi r squared. And again, that is a little tricky to do, but this one I'm going to use pi r squared. I'm going to cross off the other one. Bye-bye. I don't need that. I'm going to do the area formula. But I'm also going to do what I did in the previous video, and particularly with these problems. I'm going to set up r equals, I'm going to set up dr dt equals. I'm going to set up a equals if I need it. I'm going to set up dA dt. Okay, so I'm always going to have that little box because that just helps me kind of organize my thinking. Okay, so R. Let's find these values and see if we can plug anything in right away into our box. Notice I'm not even setting up anything else. I'm not doing any derivatives. Right now I'm just setting up. So let me go back here, set up an equation, go with the word problem, then set up variable values. Anything with a rate is a d something dt. And then after that, take the derivative with respect to time, plug in values, and solve. Okay, so what we're going to do here is we're going to take the derivative a equals pi r squared, and let's go and do that. The derivative a equals pi r squared is going to be dA dt with respect to time. Is going to be, remember that pi, nothing happens to that. So pi times, the derivative of r squared is 2 times r times dr dt. Okay, now I actually didn't set up the values because I'm kind of multitasking here. Okay, and we are going to go ahead and get some values here. The first value that I saw when I was reading through this problem is the radius increases at a rate of 4 centimeters per minute. This has to be a dt. The reason it has to be a dt is because it has minutes there. And it says the radius. So the radius is changing, which means it's dr dt. Dr dt is going to be 4 centimeters per minute. dA dt doesn't have anything. R is 5. It tells us R is 5 right here when the radius is 5 centimeters. So I can plug in these values here. R is going to be 5. dA dt is going to be equal to 4. And I'll be able to get my answer. I'm going to multiply this all out, and I get dA dt equals 2 times 5 is 10 times 4 is 40, so I get 40 pi. Now note the units. It's going to be area changes at centimeters squared per minute. That's your answer to the first one. These are going to be definitely doable, but might take some work and some time in the setup. The setup is going to be the big key for all these. I'm going to do B and C. Actually, let's go to C. Let's do C first. Oil spilled from a ruptured tanker spreading in a circle on the surface of the ocean. The area of the spill increases at a rate of 9 pi meters squared per minute. How fast is the radius of the spill increasing when the radius is 10 minutes? Go and try this on your own and see if you got this. And I'll start the problem up in another minute. Try it. If you're waiting for me to actually explain it, you might be going in circles right now. Okay, no, seriously, you should try it. Okay, they want dAdt. That's what we're going for here. I'm going to set everything up just so you can see how it is. It said R is 10, but I need to know dRdt. And dRdt looks like it's going to be about, I don't know. A, I don't know. And I didn't need to know it in the last problem, but dAdt, it says is 9 pi. Oh, but I want to know how fast the radius is changing. Okay, so how fast is the radius means that I am looking for dRdt. That's what I'm trying to solve. So let's take the derivative. And I hope you're able to get that on your own, but that's me talking through it. I got dAdt equals, it's at pi again, so don't worry about the pi. Bring the 2 down, 2 times r, that's a power rule, times, I just took the derivative of the radius with respect to time. By the way, for that a, I took the derivative of a with respect to time, which is why I got that dAdt. I'm going to plug in values that I have. dAdt was equal to 9 pi, so let's go and plug in 9 pi in here. So I got 9 pi equals, let's go and do pi times 2 times r, and r is 10. So times 10 times dRdt, and that's what I'm trying to solve for. dRdt, don't know what that is yet, but I think I can solve that now, because on the right side I get 20 pi. If I divide that over, I get 9 pi over 20 pi, and that's my answer. dRdt is equal to 9 pi over 20 pi, which is really 9 over 20. And your units are going to be meters per minute. How did we know it was meters per minute this time? I knew that this radius was changing with meters per minute is because it's not meters squared. Meters squared is area. So I'm going to just jot that down here. If we have something squared, that's area. If we have something cubed, that's volume. And if we have just something to a first power, that's going to be that linear dimension. That could be meters or centimeters or just inches, feet, any of those one-dimensional units. Okay, that was C. Let's go and try B now. And I think that kind of takes care of it. I want to see if there's a ladder. Let's do G, and then that's it. They have answers here for the rest, so you're welcome to try the rest on your own, but I'm only going to do 2 more. The edge of a cube is changing at the rate of 300 cubic inches per minute. I just said that cubic inches per minute is going to be volume, but it's a rate, so that means dV dt, if I'm just doing my box off to the side, dV dt is equal to 300. I didn't even read the problem yet. The volume of a cube is changing at the rate of 300 cubic inches per minute. Find the rate of change of the edge when the length is 10 inches. So we got a length of an edge. I'll just say that's L. So L is 10. But if the volume of the cube is changing, that length has to be changing. So let's just do dL dt. And it looks like it says find dL dt, so we don't know what that is. It also says the volume here. Actually, I don't know what the volume is. And do I have to know? I don't know. I don't know if I need to know the actual volume of the cube at that time. I don't think that's going to help me take the derivative. Because let's see what happens. A cube's formula for the volume is just going to be the length or the side length cubed. So when I take the derivative with respect to time of the left, I get dv dt. When I take the derivative of the right side, I get 3L times, I just took the derivative of the length of the edge with respect to time, so I have to do dl dt. Notice that this equation here, I actually don't need v, so I'm going to cross that off because there is no v in this equation. There's a dv dt, but dv dt is very different from v. One is a rate and one is the actual value of the volume. All right, now we're going to go and solve, plug numbers in. I got dv dt is 300. I'm going to drop the colors here. I have 300 is equal to 3 times L, which is 10, times dl dt. And 3 times 10 is 30. If I divide that 30 over, it looks like I get 10. Is that right? Yeah, 10, which is equal to dl dt. And what are your units? Are your units squared, cubed, no unit, 1 unit? Because we have the length of the edge, then I'm just going to 10 inches. So the length of the edge is increasing at 10 inches per minute at that particular time. All right, we are going to skip D, we are going to skip E, and we are going to go to G, and that'll be it for this video. A 5-meter ladder is leaning against the side of the house. I want you to try this problem on your own just with the setup. I'm going to go back to this page just for the setup and see if you can get an equation going for how this problem is going to work. Go ahead and try the problem. I'm trying to climb up that problem. You might need a ladder. Just kidding. Okay, let's go on and try the problem now in like a minute. Or like 5 seconds. Okay, let's go and do the problem here. We got G. We're going to do a 5-meter ladder leaning against the side of the house. Okay, here's time for my art skills. Here's the house. Here's the ladder. Ooh, it leans at a right angle. Oh my gosh, I made a triangle. And the foot of the ladder is being pulled away from the house at a rate of 0.4 meters per second. Now, the first thing that I want to tell you about this problem is being pulled away from. When I'm pulling away from the house, I am actually, that distance at the bottom is getting longer and longer and longer, which means that 0.4 is positive. I'm going to type a note here because that's an important aspect of the problem. If you label that as negative, it's going to be wrong. So foot of ladder is getting farther and farther away from the wall, which means that the rate must be positive. Okay. And by the way, if you drew it a different way, it would be the same thing. I'm just going to draw this again for you just so you can see it's the same exact thing. So if I drew it this way, that's my house. I don't know why I have an axis here. I don't know why I have beneath the floor. If I have the house there and then the ladder this way, the rate of the ladder's movement is still moving. The foot of the ladder's distance is still increasing. It's still getting farther and farther away from the wall, which means that rate is still going to be positive, no matter how you draw it. Now, at the same time, the top of the ladder is going to be falling and getting closer to the ground. And because the top of the ladder is falling and that top of the ladder is getting closer and closer to the ground, that means its rate is going to be negative. So we should expect a negative value here. Okay, now let's go and set up. I don't know, and this is where we want to make sure we're using our variables accurately. I do not know how far the ladder is from the house as it's moving. So as it's moving, I'm going to call this x. I'm going to call the other variable y. That's going to use this variable. And I'm going to call this third one z. I'm going to set up an equation because I think I got an equation from that. I got x squared plus y squared equals z squared, right? That's an equation. X squared plus y squared equals z squared, okay? Now I'm thinking about this problem and I'm thinking, okay, what's going to change here? So which variables are going to change? I'm just going to put this in purple, this color. And which variables are not going to change? Well, the variables that are going to change are going to be x's and y's. The z is not changing. The z doesn't change because it's a ladder. Ladders don't change size when they're fallen. So I could plug in the value here and get a rate. What I'm going to do here is first of all set up my answer, my numbers. So let me just get rid of this box. Let me go and put a box in here. All right, so I'm going to go ahead and set up my values. I have x is 3 meters. Y is, I don't know. I have z is 5 because that's the length of the ladder. If x is 3 and z is 5, if I plug that into the Pythagorean theorem, I get 3 squared plus y squared equals 5 squared. That means y has to be 4. I'm going to trust that you can finish that up on your own. That's a little bit of review of geometry. Now there should be a dx dt, there should be a dy dt, and there should be a dz dt, because each variable might be changing. It tells us that the foot of the ladder is pulled away from the house, which is at 0.4. So the foot of the ladder is 0.4 and it's a positive one. We are trying to solve for dy dt, that's the value that we want. And what is dz dt? I think I said it already, but the rate that the ladder is changing at is nothing. That ladder can't change. So now let's go and take our derivative. The derivative of x squared is 2x, but I took it with respect to time, so that's dx dt. Plus, the derivative of y squared is 2y, but I just took that with respect to time, that's dy dt. The derivative of z squared is 2z, but I just took that with respect to time, and that's 2 dz dt. And now, let's have fun plugging in numbers. I'm going to get 2 times 3 times 0.4 plus 2 times 4 times dy dt, don't know what that is, that's what I'm solving for, equals 2 times 5 times 0, because the rate of the ladder is not changing. It looks like I'm going to get 2.4 on the left if my math is correct. If it's not, don't tell me. I got dy dt on the right here. I'm going to move that 2.4 over to the other side, and I get negative 2.4 over 8, which looks like it's going to be some fantastic number. 8, negative 0.3. I actually knew it was negative 0.3, but I just didn't want to say anything. And the units are meters per second. Please make sure you're putting your units every time. Thank you for watching the video. I hope it was helpful. Have a good day.